న్యూటన్ పుట్టకపోతే మన పరిస్థితి ఏంటి? థామస్ ఆల్వా ఎడిసన్ అనేవాడు జన్మెత్తకపోతే ఈ ప్రపంచం ఏమయ్యేది? అసలు ఈ ప్రపంచంలో ఉన్న మేధావులు అందరూ పుట్టకపోతే మనం ఏమైపోయేవాళ్ళం? ఎప్పుడైనా ఆలోచించారా?
వీడు పుట్టకపోయింటే హాయిగా ఉండేవాళ్ళం.
అక్కడ అనవసరంగా పుట్టింది.
Manoj, am I audible? All right. So I think we are going to be having two more classes, including today's class. And since the course is basically based on your introduction to VLSI, remember the transistor properties are very, very critical and important to understand. And as we have shown in the previous classes, as well as in the examination, I did put in a question that kind of relate any kind of combinational circuit or any kind of Boolean expression in form of your inverter. And we also said that the inverter also can be translated to make into the universal gates, which is NAND and NOR. And so that kind of made it very, very important to understand in detail about the inverter properties. And that is how we started to talk about and study in detail about inverter. So whenever we are talking about the CMOS inverter, the whole idea is to understand the basics of your CMOS inverter. So whenever we talk about CMOS inverter, it essentially means that you have an input and then you have an output, and the output is just the reverse of your input. So that is the first point. So that basically caters to the functionality part of it. And then if you go into detail, you have to talk in terms of the output with respect to input when you have the voltage as a DC source, right? So whenever you talk about the output, whenever you talk about the output of the inverter when the source is DC, it is basically talking about the static behavior, because in that DC, either it is in the VDD is either at 0 or is high. So the high voltage would depend upon different technology nodes. Remember, we have also talked about scaling. So the transistor and the scaling part needs to be well understood to further a cause for inverter and then for all types of computational or sequential circuits. So if we are able to understand inverter in detail, and it's in terms of not only functionality but also in terms of transfer characteristics. We did mention about the transfer characteristic and specific voltage transfer characteristics in our last class. So we'll just try to revise that and then build up on that. So whenever we are talking about the voltages in static behavior, we are talking in terms of output with respect to our DC bias. We have yet to talk about what happens when the behavior is dynamic. So dynamic would mean some kind of an AC signal, some kind of an AC signal in which there is a transition from high to low state or low to high state. So the whole transition happens. We are not talking about when the voltage is static, when the voltage is dynamic. Okay. So in the voltage transfer characteristics, the IV characteristics are determined or uh, uh, or watched upon at the output of the inverter. So we shall be talking about some of the other important points. We have also talked about the so-called switched model. Last time I think we did talk about switched model in our static behavior. So I think we took the reference from, can you see the slides? From the NPTEL lecture notes from the professor from IIT Roorkee. Can you see the slides?
No, sir.
Can you see the slides? Hello?
Yes, sir.
Yeah, so basically, the basic idea of CMOS inverter is very, very critical as it is a build up to any kind of combination and sequential circuits. And then we talked about the switch model of the inverter. We also mentioned about static behavior. By static behavior, essentially means output with respect to your DC bias. And whenever we are talking about static behavior, by uh, static, as the name suggests, when the voltage is either at absolute zero or is at the high state. Then we went on to talk about the voltage transfer characteristics. Okay, so I think we kind of introduce you to this voltage transfer characteristics last time itself, which was essentially the current voltage characteristics at output of the inverter. Then we talked about the switching threshold. Switching threshold, I think we did not talk in detail. We need to talk about all these aspects in detail in this class and then subsequent class. So whatever was not finished, we shall be talking on those lines. So switching threshold, which is actually coming from your voltage transfer characteristic curve, and we need to talk about the noise margin of an inverter and the overall gain calculation. Remember, the gain calculation in digital is not the same as the gain calculation in your analog circuit application. So there we talk in terms of transconductance and stuff like that. So here it would be the basic definition of the gain is always the same, but otherwise, which is like your del V out by del V in, so change in the output voltage versus the change in the input voltage, but its determination and the parameters are somewhat different. So gain is an important parameter both in terms of digital and analog, but more importance is given in your analog application because you want to amplify your signal. Okay, so we shall not be touching on the analog aspect. We shall be only talking in terms of a digital aspect. So digital aspect, essentially the building block happens to be these inverters. That is why I asked you. So, how many of you actually finished with the Boolean expression that we had talked last time? Hello? Hello? How many of you actually tried to express the Boolean expression in terms of PMOS and NMOS, or in terms of remember, there will be a question of that, and it will be kind of not so simple, and it would because that basically helps you to understand that how any kind of logical expression or any kind of combination or a sequential circuit, a part of a sequential circuit, can be realized using CMOS. which essentially constitutes of your PMOS and NMOS. So to understand all these things, first of all, we need to know the basic characteristics of a PMOS, the basic characteristics of your NMOS, sorry, and as an inverter, how does it work? So you need to know when does your transistor, PMOS transistor conduct, when does your NMOS transistor conduct, what are your short channel effects, what are your secondary effects, what happens when you are scaling it down, and the input output relation when you realize it in form of inverter or the other universal gates. Okay, so the basic idea we had talked last time, it was essentially the PMOS, which is your, can you see this, or should I just, hello? Hello?
Yes, sir, we can see.
Yeah. So the basics of your CMOS inverter is somewhat like this. You have a VDD and your ground, which are the source of your PMOS. So this transistor M2 at the top is your PMOS, and the source of your PMOS is connected to your VDD. At the bottom, the source of your NMOS is connected to ground. The gate of both PMOS and NMOS are connected to each other and to the input signal, while the drain for your PMOS, which is M2 at the top, and NMOS, which is M1 at the bottom, the drain is connected to each other and to the output, and also to the load capacitance, where when there is a direct supply from the VDD, it gets, the load capacitance gets charged up. So this load capacitance and the overall capacitance of this inverter configuration we shall study in detail at a later stage when we are talking about the dynamic characteristics. So here in the initial stage we are talking about the static characteristics or the static behavior. So in the static behavior, remember the output with respect to your DC bias, and in the dynamic when it is, you know, switching from 0 to 1 and 1 to 0. Okay, so that we shall be talking at a later stage. So there, this capacitance will play a very important role, because you are also talking about the propagation delay that is happening due to the inverter or inverter stages. So this is one inverter, and if it is connected to the next stage of inverter, then it becomes cascaded. So if you have a cascaded kind of configuration in which you have a chain of such inverters one after another, you shall be talking in detail about the overall capacitance that is coming out from a single stage of your inverter. Okay, so there you would be talking in terms of equivalent capacitances and equivalent resistance that are offered by your CMOS inverter. So studying the single stage CMOS inverter at both when you have static behavior or the dynamic behavior becomes very critical. So we have already talked what happens when you give a static voltage of Vin equal to 1, or when you give Vin equal to 0. Remember, I'm just trying to revise and remind you all these things so that we can build up and try to finish both the static behavior and dynamic dynamic characteristics of a inverter, CMOS inverter. So when you have this Vin equal to 1, then what happens to your PMOS? When your Vin is 1, then let's start. Anybody? Hello? Yes? Hello?
Yes, sir.
So what happens when your Vin is say 0, at 0, constant 0, or at constant 1? Let's start with say, what happens when your Vin is constant 0? So Vin is connected both to M2 PMOS and M1 NMOS. So if it is 0, your PMOS would be in the conducting state, while your NMOS is in the cutoff state. So there will be a direct supply from your VDD to your V output. What happens when your Vin is equal to, so basically your output would be equal to 1. What happens when your Vin or the voltage at the gate for M1 and M2 are at static 1? Your PMOS comes into the cutoff region, while your NMOS is in the conducting region. So there is a direct line between your V output, where you have a charged load capacitor, and your ground. So the capacitor C load starts getting discharged till the point it reaches ground. So it forces the output to go to stage 0. So this is how your inverter is working. And we already know how do you get the output when you have NAND and NOR gate, which is an extended configuration of your inverter series, in which you make these PMOS and NMOS to work in either a series combination or a parallel combination. Is that clear? Hello?
Yes, sir. Yes, sir.
We also talked about the CMOS inverter as a switch model, in which we did mention that what happens in the switch model? When your input is high or VDD, your NMOS is in the on state, while PMOS is in the off state. So your NMOS acts as a resistor, while a PMOS acts as a switch. Okay, so while in the other case, when your input voltage to the gate of PMOS and NMOS is 0, your NMOS is in the off state and the PMOS is in the on state. So basically, the top configuration, which is having PMOS, is also sometimes called as the pull-up network, because the capacitance CL, which is getting charged, the charges are basically being pulled up from the source VDD, while the NMOS, bottom NMOS network, is also sometimes called your pull-down network, because here we are just talking about a singular NMOS and PMOS, while in any kind of combination circuit or digital IT circuit, it would be a series or parallel combination of your NMOS and PMOS transistors. So the bottom NMOS is generally called your pull-down network, because it pulls down the charges from the load capacitance to the ground. So it's basically called the pull down network, while the top PMOS configuration is called the pull up network. So we have already talked about the static behavior. We had already initiated. Some of the other important things that needs to be taken care of is that most of these inverter would require high noise margins. For that, we need to understand what exactly is a noise margin. The other important characteristics of a CMOS inverter in when you have the static in a static behavior form is that it has a ratio-less logic. Now, what does ratio-less logic mean? Anybody? Anybody? Hello? What does ratio-less logic mean? Again, the concept is coming from your basic definition of your transistors working in linear stage, saturation stage, and cutoff stage. And when you're comparing the PMOS with your NMOS. So there, if you see the IDS value and the relation in the three regions of operation, you would have a factor W by L. Okay, so that would essentially talk in terms of your ratios. Are you there with me? Hello?
Yes, sir.
Then in your CMOS inverter, the output impedance needs to be low, which would facilitate your inverter to be less prone to noise. So as in the transistor, I think you may have studied before, and if not, then just get some idea, because you need to know what are the different types of noises that are generated in a transistor mode. And then that, since inverter has both NMOS transistor and PMOS transistor, so it will also have certain noise like your flicker noise, like your junction noise, like your thermal noise, etc., which are being generated within the transistor system. And when you are making into when you are translating a circuit like your NAND circuit or your NOR circuit out of it, so you would want this CMOS also, which is being made up of your two different types of transistors, which is PMOS and NMOS, to have minimum noise. Okay, so output impedance essentially being low facilitates that. And if you have higher impedance, as you can see, it improves the number of your fan out, which we have defined last time. That what is a fan out essentially? So fan out basically is, as you can see, is when is the capability of your single transistor to drive any number or n number of next stage devices. Okay, so a higher impedance coming out of high impedance would kind of facilitate the improvement in terms of your panel or number of stages that a single device can drive. Okay, and then you would want no static power consumption. So basically, whenever you're talking about static power consumption, you're essentially talking about the leakage current. So this static power consumption needs to be taken care of. And this static power consumption in a CMOS inverter, when we talk in terms of its static behavior, shows almost no value. That is why the CMOS inverter becomes very ideal, since it has almost no static power consumption. So remember, this power consumption is a very critical stage because the number of transistors per unit area is increasing by the day. So the power consumption also increases by the day. Remember, the number of transistor is almost getting double because the industry, the semiconductor industry or the IT industry is stretching to follow the Moore's law, which states that every 18 to 21 or 24 months, the number of transistors should kind of double, right? Yeah. So we have also talked about this CMOS inverter as a voltage transfer characteristics. Remember the behavior of your NMOS and PMOS. So essentially, what we are doing is you have a PMOS and an NMOS and its IV characteristics. We are trying to translate on the same axis. So essentially transforming the PMOS IV transfer characteristics on the same coordinate axis. So this is how you get it at the final stage. So you have, first of all, the mirroring of your stages. Okay, so this is your P stage, and then you have the horizontal shift over your VDD. So finally what you get is this. So this is what is the equivalence of your PMOS and MOS IV characteristics of your transistors being translated on by your mirroring of your mirroring and then the horizontal shift over your VDD. So CMOS voltage characteristics can be achieved by superimposing of your drain current, yeah, ID versus VDS, of NMOS and PMOS onto the common coordinate plots. So this is what is your voltage transfer characteristics. Okay, so we have also talked about the VTC curve, and then even this graph we have talked last time, which is the CMOS inverter voltage transfer characteristics. Why can't I make it bigger? Class? Class? Are you there?
Yes, sir. Yes, sir.
Yeah. So this is This is the CMOS inverter voltage transfer characteristics, and you can see on the left hand side you have the NMOS transistor, and your gate voltage Vin is increasing, and here on the left hand side, so this is the right hand side. Can you see the cursor? Can you see the cursor? So the one which is, to me, one which is on the left hand side is the IV characteristics for the PMOS, and on the right hand side is the NMOS characteristics, the IV characteristics for your NMOS. And you can see that as the gate voltage is increasing, so is the drain current in for your NMOS configuration, and the drain current is decreasing for your negative voltage for your PMOS configuration. So what are we interested when we are talking about static behavior is either the stages both at the extreme ends, which is this region and this region. In between region, we are not interested when we are talking about inverter or any kind of digital application. So the CMOS inverter voltage transfer characteristics VTC can be seen from here, in which you have almost 5 stages for an inverter configuration. The first stage we have already talked is when your NMOS is in off state and your PMOS is in the linear state. Remember, there are 3 stages of your transistor operation. The first one is the off or the cutoff stage. The second one is when it is showing a linear behavior. And the third one is your saturation state. Okay. So for digital application, we would never want our transistors to work or be in the third stage, which is ideally your linear state. So we talk of either cutoff stage or in the saturation state. But when we are talking in terms of inverter, we have both PMOS and NMOS, and if one is in a particular stage, the other happens to be either in the bang opposite state or any other state other than the one in which the other transistor is working. So if you see here, there are 5 stages. First stage, your NMOS is off, PMOS is in linear. Second stage is NMOS is in the saturation, PMOS is in the linear. Fourth stage is when your NMOS is linear and PMOS is in saturation. And in the final stage, what you have is, which is 5th stage, you have NMOS is linear and PMOS is in the off stage. So as an inverter configuration, when you have static, you are interested only in a region which is either this or this. And then in between you have a situation where your NMOS is in saturation as well as PMOS is also in a saturation state. So ideally this state you would like to avoid, or you would like to squeeze down. So ideally it should be a very sharp transition from high to low or low to high. So in between stages you would never want to appear in so-called VTC curve. So this transition region, which is the in-between region, can you see this slide? Hello?
Yes, sir.
Okay. So this in-between region, this part, where both NMOS and your PMOS starts to get into saturation stage, and it extends up to a stage which is making either NMOS in saturation and PMOS in linear, or NMOS in linear and PMOS in saturation is your transition state. And this needs to be avoided or minimized. Okay, so the region where both PMOS and NMOS are in a saturation state needs to be avoided or are not required, as this region is very unstable. The region 2 and 4, in which one of the transistor is in saturation while the other one is in linear, or vice versa, happens when your gain del V out by del V in is equal to -1. So another important parameter which you can attain from this VTC curve is what you define as the so-called switching threshold, Vn. So switching threshold Vn can be obtained from the VTC curve. So this is the VTC curve. When your V out becomes equal to V. So this VTC curve is the curve between input voltage and the output voltage for an inverter configuration. So switching threshold voltage is an important parameter which is obtained from, please note down, these are, we shall be asking about switching numerical based on all these things. Yeah. So the expression here is already there. Please note down. Please note down. So this expression you need to note down to determine the switching threshold voltage. Have you finished? Have you finished? Class? Manali? Manali? Saivikas? Manas? Please say yes or no. I need to kind of. Okay, fine. So Manas says yes, I assume everybody. So basically from this you can actually see that there is a relation that is happening which is defined by your R parameter, which is the ratio of mu p by mu n. And remember, mu n and mu p are very different, which is the mobility of your electrons to mobility of hole is different. So essentially, to uh, uh, to have a kind of a symmetric Vn, one would want that your transistor sizes to be manipulated in such a manner that you are able to achieve your goal. So essentially, most of the times, your Vm, which is your switching threshold voltage, is equal to VDD by 2, and this happens when your PMOS is 2 to 3 times larger than your NMOS. So basically, one needs to play with the W by so here you can see WP and WN. So the width of your PMOS and your width of your NMOS is something you can play to achieve this goal. So we also talked about, we shall now talk about the noise margin in your CMOS inverter, which is a very important factor. We would essentially want to have a good noise margin for our inverter configuration. Okay, so remember we are still talking about the static behavior, when either the input voltage is 0 or input voltage is 1. Okay, so before that we need to know how do you actually determine the noise margin for any kind of digital circuit. So noise margin, as we have mentioned last time, is defined by noise margin low and noise margin high. So if you have, say, input, you have a logical high input range, and then you have a logical low input range. So it will have a particular output. Any kind of digital circuit would have a particular output. Again, which would have a logical high output range and a logical low output range. So logical high input range is define the difference between the VDD and your NMH. Let me just expand this. First of all, you need to know what is, just a minute. How do you define and how do you determine the noise margin for any kind of digital circuits? So if you have input and output characteristics, the logical high input range goes from VDD to VIH, and your logical low input range goes from VIL to your ground, while your logical high output range is from VDD to VOH, and logical low output range is from VOL to ground. Okay, so for your inverter configuration, you would again have the same method to determine the noise margin. So noise margin high and noise margin low is defined as the difference between VOH minus VIH for your noise margin high, and noise margin low is defined the difference between VIL and VOL. So for this inverter configuration, since the VOL equal to 0, so your VOH is equal to VDD, and VOL is equal to 0. So your NML is equal to VIL, and your noise margin low is equal to VIL, and noise margin high is equal to VDD minus VIH. Please note down. So this will help you to determine the noise margin for inverter, which at a later stage would be also translated for, say, a series or cascaded stage. Remember, from a single inverter, you can make by using it in a series formation, you can make a buffer. Okay, and you may have series of such buffers, which is basically what you call as the inverter chain. So here, to understand digital IC design, we need to first understand the properties of and behavior basically of your inverter and relays of inverter, or cascaded inverters or inverter chains. So first we need to understand of a single inverter, and then it will be gradually expanded to the cascaded inverters. So if we know how to determine the noise margin for a single stage CMOS inverter, we shall be able to translate, and this would help to determine various parameters. Hello? So what exactly is a noise margin? It is the amount of noise which the inverter can reject without affecting the so-called output. Okay, so noise margin is very important because it actually gives you the idea of how much noise your single stage inverter in this case, or your kind of a digital device or your digital circuit is able to reject. So inverter happens to be beneficial in so many ways. It is also a very good noise rejector. So if you are having a higher noise margin, it will lead to a better noise rejection. So that is the key point. Why are we doing this determination of noise margin? Is to see how much good as a device it is to reject the noise. We have talked about different types of noise, and that not only comes from the internal transistor configuration, but all kind of interconnects. Have we finished with this? This is very important. Hello? Can I move to next slide? Hello? Yes, okay. So this they are trying to determine the VIL calculation. So that is just by making Vin equal to VIL and NMOS in saturation region and PMOS in linear region. We have this dV out by dVin equal to -1, which is what we have seen when your NMOS is in saturation region and PMOS is in linear region. From there, we kind of determine the different values. Right? So VIL is finally given by this expression. So you should note down this. You should note down this. VIL is 2 times V out plus VTP minus VDD plus KR VTN upon 1 plus KR, where KR is equal to KN by KP. So what is Kn by Kp? It is mu n Cox W by L of divided by, so basically for n, and mu n Cox W I L by for P MOSFET. So n basically stands for N MOSFET and P basically stands for P MOSFET. Similarly, calculation of your VIH. So that happens when your NMOS is in linear region and PMOS is in the saturation region. So ultimately When you have dependent VIH, then you also determine the switching threshold VM. So that happens when the both transistors are in the saturation region. So PMOS and NMOS both are in saturation, right? So for PMOS, we know the saturation, we know the current equation in the saturation region. For NMOSFET, we again know the current equation IDS in the saturation region. So we kind of translate that here and determine the VM. So please note down the value of your VM, where R basically stands for KP VD SAT. So voltage in saturation region for P, KP we have already defined, UNC of W, and Kn we have already defined in your for your saturation voltage of your NMOS transistor. So this is your final expression to determine the switching threshold. And if you carefully see, this VM is dependent on the structure of the device. So it is dependent on the structure. So essentially you are having all these parameters like W and L, and so that is playing a major role. So it's 12, 1 hour is left. I need to also switch to so please note down this. So how it is determined? You achieve a switching threshold when V in becomes equal to your V out. Now another important parameter, which is voltage gain. Voltage gain. So voltage gain is essentially, the expression is here, and it is almost purely determined by the technology parameters and needs some manipulation in the transistor sizing ratio. So generally when we talk about transistor sizing, we are talking in terms of the W by N, which is width of the transistor and the length of the transistor. And lambda, this lambda which is coming, it is essentially coming because of the second order effects, which is your CLM, channel length modulation. So this gain parameter is process dependent and also happens to be an important parameter for your CMOS inverter and its behavior in the static mode. So ideally, you would want your gain to be on a highest, your noise margin to be on the highest. Since gain is del V out by del V in, which is output versus input, change in the output voltage versus change in input, it would have a detrimental effects also on the delay. Delay is happening on the load side of the capacitors at the output. Why? Basically because it is a capacitor, and the capacitor charges and discharges because charges and discharges, and it delay is dependent on the RC constant, which is the resistance and capacitance, which is related to your overall, which is related to the voltage. So there is basically a trade-off in terms of gain, in terms of noise margin, noise, which would be helping you to reduce noise, and the overall delay in the inverter configuration to actually realize the behavior of the inverter in the static mode. So please note down the expression for gain G. And this is some typical output. Again, you can see this is from 2.5 to 0.5, and then if you and then again from 0.2 to 0.05. So this part, this transition part, is better for higher voltages. Better basically means it deteriorates when the voltage goes down. So that transmission becomes bigger and bigger, which is not expected in your digital circuit, including the inverter, CMOS inverter that we are talking about. So these kind of outputs you can see from tools like Synopsys or Cadence, which is used mostly in the industry. So they will ask you to kind of design using either to have better gain and this thing. So this is a very simple, this is the basic building block. So first you need to know how to make a good inverter, then maybe a good NAND gate, and then any kind of multiplier, 16 plus 16, or any kind of multiplier, adder, subtractor, so on and so forth. And so you have to consider each and every parameter, and if there is some kind of a conflicting parameter in which because or contradicting parameter which basically deteriorates the important characteristics of your digital circuits, then you have to basically do a trade-off. That trade-off can be in terms of your process, that can be in terms of your structure of the transistor device. So CMOS inverter consists of a PMOS, which is a pull-up network block and a pull-down network block, and I think this is just trying to see. And gain of an inverter is function of your technology parameter. And the logic string, which is like talking about 0 to 1, is equal to, or 1 to 0, is equal to the supply voltage and does not depend upon the device, relative device size. So these are some of the inferences from those equations that we have already seen. And an ideal inverter exhibits a high input impedance and a low output impedance. Now we go further to talk about the dynamic characteristics. So what is dynamic characteristics? It is essentially talking about, going from, it's not static in nature. It's not 0 and 1. When you be not is not static at a voltage, is not static at a particular voltage. So if it is having a transition from 0 to 1 or 1 to 0, so that would essentially lead to the propagation delay. So propagation delay is generally denoted by T. And the moment you are talking about propagation delay, it will also talk in terms of any delay has the RC component. So one needs to determine the RC component in the inverter configuration. So we need to know equivalent resistances and equivalent capacitances in an inverter configuration. And to determine the propagation delay in a dynamic. So how do you define a propagation delay? It is the difference between 50% of the input rise to 50% of your output fall. Okay? So in this part, when we are starting about the dynamic behavior, we shall be talking about sizing of the so after this we shall be talking in terms of sizing of the inverter. This will happen when we are talking about cascaded inverters. You are having more than one chain of inverters. Okay, so first, and in that we shall be particularly talking about optimization of the size of the inverter chain. Then we shall talk about the dynamic power dissipation, source of leakage, the static power dissipation, and the product delay and energy delay product. So power delay product and the energy. So PDP and EDP. Power delay product and the energy delay product. Yeah, so this basically is talking about the propagation delay, which we have already defined. The difference between the 50% of input rise to 50% of the output fall is basically giving you the value of your TP. So the equivalence of your resistance is determined by, remember, using this model. Okay, so from there we are able to get the overall value of your resistance or your R equivalent, and then you have two other parameters, which is the propagation delay from output to go from high to low, which is TPHL, and propagation delay for output to go from low to high, which is TPLH. Okay, so the overall propagation delay is TPHL plus TPHS by 2, which is you are having 0.69 load capacitance plus the equivalent resistance for your N configuration and equivalent resistance for your P configuration divided by, so please note down. So this is for the transient response, or basically when you're talking about the dynamic behavior for your inverter configuration. Hello, you there? Banod, are you there? Manas, Tarun? Okay. So to determine the overall, so to determine the delay, we need to talk the propagation delay. We need to talk about equivalent resistance and equivalent capacitance. So now we talk about, say, a two-stage inverter configuration, which you can see. We need to determine the overall capacitance, calculation of the capacitance. So this calculation of capacitance is a very important parameter, and there may be a numerical based on this, because we will be having a numerical based on propagation delay. So here you are seeing two back-to-back inverters, which is a kind of a buffer or a cascaded inverter, one after another. So the output goes to the input of the second stage. So what is a cascaded configuration? You have two inverters back to back, or in series, in which you have an input and the output of stage 1 is going to the input of stage 2. Okay, and then you have output of the stage 2 inverter. So as you see, in between the two stages, you have a load capacitance, or also the wire capacitance. In between the two, you have the wire capacitance, and the overall load capacitance, because of this cascaded configuration, can be break down into the following components. So the load capacitance would essentially constitute of first stage, or inverter in stage 1, the gate drain capacitance GDB12, which is this GDB, sorry, just gate drain capacity. Yeah, GDB 1, 2, this one. Then you have GDB 1, 2, which is basically your diffusion capacitance. So gate drain, GD stands for gate drain, capacitance between gate and drain, 1, 2. Okay. Then you have GBB, which is drain body, 1, 2. Okay. So for 1, 2 basically means for 1 and 2. So there are two types of, there are two components of your diffusion capacitance. So the body from here, GDB 1, 2, this is GDB 1. So this is GDB 1, 2. Then you have CW, which is the wiring capacity. And then you have the capacitances G3 and G4, which is the gate capacitance of the fan out, which is this. So you need to, so your new CL load capacitance would be having these four components. So here you are taking of only, you're talking of only two stage. Similarly, as you extend the number of stages, the load capacitance may change according to the new configuration. Yeah, so I think to calculate the capacitance for this cascaded inverter, you have both M1 and M2 in stage 1, either in saturation or cutoff region. So under this condition, only gate drain capacitance is CGD1, which is drain C capacitance between gate and drain. Because the signal string is opposite in both terminals, the effective capacitance would be twice, where CGD gate drain is equal to the overlap capacitance per unit width. So it's just explaining the different types of capacitances to get the equivalent capacitance of your two-stage inverter, which are cascaded. So we are able to determine the gate drain capacitances, the diffusion capacitances. Remember this gate drain capacitances, there is also a relation with your so-called Miller capacitance. So you need to use your previous knowledge. Then the other two components You calculate your overall capacitance, are your wiring capacitance, and the gate capacitance of your fan out. Since the fan out is 2 here, oh sorry, fan out is 1. Yeah, there is one inverter which is at the output. So fan out is 1. Yeah. You find out the equivalence fan out capacitances. Yeah. So once you are able to determine the equivalent resistance and capacitance, the goal is ultimately to reduce the delay, which is where the design engineers come into picture. So that can be done by reducing the CL, by playing around with different parameters, or by again designing the transistor using all those cadence or synopsis tool in terms of your aspect ratio or transistor sizing W, L, that takes care of the self-loading, or by choosing the transistor parameter and to play around as a design or device engineer to increase the VDD, because by increasing the VDD you can force the capacitor to charge and discharge in a faster manner, but it would also have a negative effect. So again you need to do a trade-off. Why? Because more VDD basically means more energy dissipation, right? So here the role of your design engineer comes to picture. So this is for a very simple two-stage inverter or a cascaded inverters. Please note down these parameters. Yes, are you there? Manali, Tarun, Sai Vikas. Banot.
Yes, sir.
Okay. Please note down. Sorry. So why I'm taking this classes at least to inverter level, designing an inverter. Because once you know how to design an inverter, you can translate it, because that is like when you talk about particular kind of digital combination circuit or some kind of a complicated sequential circuit. I shall also give you some insight towards the hardware discussion language tomorrow. I move further. Then we also talk about the optimum value of NMOS to PMOS ratio. So while improving PMOS with the propagation delay TP from low to high of the inverter improves due to increase in the charging current, but it also degrades the TP, which is the propagation delay from high to low due to large parasitic capacitance. So what one requires is an optimum value of NMOS to PMOS ratio. So optimization. One is because of one. There is an increase in charging current, and because of the other parameter, which would overall determine the overall propagation delay, it's a detrimental thing because of the large parasitic capacitance. So that forces us to have an optimal value of NMOS to PMOS ratio, which is also talking in terms of the W by L ratios of the NMOS and PMOS transistor. So if either you can change the L is basically the channel length, which is a technology parameter. So most of the times what you can change is the W parameter. So on and so forth. So all these things needs to be optimized to get the best value of your, or the most optimum value of your TP. So here you can see it is mostly dependent on your capacitances and the equivalent resistances, as well as the value of your beta. So beta would also help you to ultimately get ultimately play around with the overall propagation delay, or gives you the license to play around with the propagation delay, so that you are able to achieve the desired results. So please note down this value. TP is equal to 0.69 by 2, 1 plus beta times C GN2 plus GN1 times the capacitance due to the wire into R equivalent for N plus R equivalent for P upon beta. Just a moment. So please note down this. So once we have done for two inverters in a cascaded form, remember the stage one of this The stage 1 is this one on the left hand side, and stage 2 is on the right hand side. So the output of stage 1 is going to the input of stage 2. So the inverter at stage 1 has transistors M1 and M2, which are also called as your driving gate. And the inverter at stage 2 having transistors M3 and M4 are also called your loading gates. So going further, when you have a kind of a inverter chain, as we can see here, like here, again we need to focus on the sizing of such inverter chain to achieve minimum propagation delay. So to achieve this, we need to see what is the number of inverter stages and optimize for the best. And what is the optimum number, optimum NMOS to PMOS ratio? Like in 2-stage, this is N stage. But with a single fan out. So in this, the overall capacitance would be C internal plus external. So C external represents the fan out and the wire capacitance, while C internal is the intrinsic output capacitance of the inverter associated with diffusion capacitances. Okay. So to get the optimum sizing of an inverter chain, we need to determine the internal capacitances and the external capacitances, and design the sizing of the inverter to reduce the delay, which would happen because of the optimum sizing that can be determined by the IC designer. So here you can see the internal capacitance is gamma times your gate capacitance, where gamma is the proportionality factor and function of the technology. So whenever we are talking about this VLSI technology, that helps you to, that helps the designer to dictate the type of technology so as to achieve the ultimate goal to have minimum propagation delay in the case of this inverter chain. So the delay of the inverter is a function of the ratio between external load and its intrinsic capacitance F. Where F is defined as the effective fan out. Please note down there will be a numerical based on such thing, which is like inverter, inverter chain, or two stage or many stage inverter, both for static and dynamic behavior. So the sizing of the inverter change happens. So the propagation delay is due to the delay from that is coming from the first stage, second stage up to end stage. So doing a summation of all the stages to achieve the overall propagation delay, you get this value. So delay equation has n minus 1 unknowns. So minimizing the delay, find n. So to minimize, always you have to do a partial derivative and solve del Tp by the capacitances. So the best way to minimize any parameter is by doing a partial derivative and solve del Tp by del Cg j, that becomes equal to 0. So this will help you to determine size of each stage, and here is the important thing, that size of each stage is the geometric mean of the two neighbors. Like this in between inverter is the geometric mean of the inverter on the left as well as the inverter on the right. So one of the conclusion of this, while doing the sizing of inverter change, the optimum size of each inverter is the geometric mean of its neighbor sizes. This means that each inverter is sized by a factor of F, which respect to proceeding gate and has the same effective fan out. So the minimum delay through the change is given by this expression. Please note down. So whenever you're talking about n series of inverter chain or fan out of more than one, you need to have a design engineer to have minimum delay, and he will be designing and doing the sizing of inverter in such a manner so as to have the condition of geometric mean between the two neighboring, between the two immediate neighbors in terms of its sizes for an inverter chain. So the minimum delay through the chain is given by this expression, where F represents the overall fan out of the circuit. So choosing the right number of stages is for minimum delay can be determined, and the designers can then tailor make those recipes for the fabrication of the IC design engineers to follow. So in common practice, the fan out could be selected as 4, as you can see here. Now we talk of the power dissipation. So there are basically 3 types of power dissipation which we shall be focusing upon. One is the dynamic powers. So before that, in a sizing of inverter chain, one needs to look in terms of minimum propagation delay, what is the number of inverter stages, and achieve the optimum NMOS to PMOS ratio. So now we go to the power dissipation. So there are 3 types of power dissipation which is there in your inverter configuration. One is the dynamic power. So dynamic power dissipation that occurs when there is a switching between 0 to 1 state or 1 to 0 state. Then you have static power dissipation. So this dissipation occurs when the inverter is either at stable at 0 state or in the high state, which is 1. And the third type is your short circuit dissipation. So short circuit dissipation happens in an inverter configuration in a very exclusive condition where both the PMOS and the NMOS transistors are in the saturation region. So to begin with, we talk about the power dissipation. For the dynamic state or the dynamic power. So power dissipation in dynamic power, this dissipation happens during the switching activity. So one can calculate the energy stored or removed on the capacitor, on the load capacitor, EC, and this EC is independent of your transistor size. So the dynamic power is defined as the load capacitance times your VDD square times your frequency of operation, going from 0 to 1 or 1 to 0. So during the switching activity, 0 to 1 or 1 to 0. I think all these definitions you would be knowing. Can you see the slide? Hello? You already know the basic definition of energy, power, and instantaneous power. Class, am I audible?
Yes, sir.
Manali? Okay, okay. So this slide is just telling you about the energy, power, and instantaneous power matrix. Uh, so energy measured in joules or kilowatt hour. Uh, so measure of ability of system to do work or produce a change. Power is basically measured in watt or kilowatt, amount of energy for a given unit of time. Average power and instantaneous power. So average power is the average amount of energy consumed per unit time. Uh, while instantaneous power is energy consumed if time unit goes to zero. Should we stop here? Should we stop here? Class, any questions? Tomorrow I will be, am I audible or not? Mansa, Manali, Banot.
Yes, sir. You are clearly audible.
Okay, so should we stop here or just finish with this part also? Otherwise, we shall be doing energy and power dissipation in your inverter configuration and some introduction to HDL language. And there will be some kind of a programming in terms of your hardware description language in your examination. And yeah, some part also on the power dissipation. Is that fine? So tomorrow we will be winding up. Bhanot, any questions? Bhanot, Manas? Okay, I think let's end for today. Tomorrow, another 1.5 to 2 hours class, and I will also tell you what all you need to study. As in, like, what are the relevant thing. I will just try to brush up, and I will try to finish with this part and some introduction to HDL, so that again hardware description language mostly towards Verilog. So very simple programming that I will just try to introduce. Very simple, which is if you actually go through the book on digital electronics or digital logic by Maris Mono, it will be in the first few chapters. So very basic of your hardware description language, and that is in your, that would be in Verilog. So essentially there are two types of hardware description language where you actually go and see, and that is further extended and used in all these cadence and synopsis tool, and these are all commercially well-known tools which is used in the industry around the globe. So Whether you talk of Apple, Intel, Samsung, whether you talk of all kind of electronic uh, hardware which you're using in your telecommunication, or you're using in medical electronics, right, from GE, Siemens, they are using uh, these tools to design all kind of circuits for different applications. Verilog and VHDL are the most famous ones, in which a lot of people use, especially in the US. They go for Verilog. So I will have a very brief introduction so that you're able to write very simple codes uh, in Verilog. So that will be half an hour. The rest I will try to finish half hour, and then half an hour I will just brush up and question and answer. And next week we're gonna have exam. So Mansa, did you talk to students? When do we want to have exam?
Yes, sir.
When?
Sir, everyone is okay with Tuesday, 10 to 1.
Huh? Can you be louder?
On on Tuesday, 10 to 1 is fine.
Okay, fine. Thank you.
Thank you, sir.